Welcome to Engineering Numerical Methods, Module number 3, Interpolation and Curve Fitting. So we are in the part 3, Curve Fitting. So the same thing with our module. So given the n plus 1 data points, okay, so we have a pair here. We estimate the future y given x. Now, before we talk about interpolation, now we will discuss about curve fitting. In this case, we will use the least squares fit. Okay, measurement error causes data to contain a significant noise, which is unavoidable in most engineering experiments. Curve fitting allows us to find the best fit curve that can represent the data points well. This curve has to be in simple form, meaning in low order polynomial. In order to ignore the noise or for some other technical reason, such as overrepresentation or commonly the term overfitting. So we have this function f of x, and the function is in terms of the coefficients. So these coefficients were discussed in the interpolation part. So if you want to learn more about these coefficients, I'd like you to go back to the previous part of this module. Now, given this function, we force this function to fit the data points, okay, given the data points, and here we can recall the module 3.2 or the part 2, where the coefficients are polynomial coefficients where m is less than n for n plus 1 data points. However, in this module, those coefficients can also be represented by exponential function in its the coefficient and exponent values. So for example, we have coefficient a of 0 and then we have a1. So it's not like the same with the polynomial where both coefficients are in different terms. Here you can see two coefficients in the same term. Hence, the form of f of x is determined beforehand based on the experiment from which the data are generated. So if you look at your data points and you will see an exponential decay or exponential growth, then you might probably need an exponential function, but most of the time it can be represented also by polynomial coefficients. Okay, so a commonly used measure, least squares fit, minimizes this following equation. Okay, we have this equation, right? So with respect to the coefficients a of I, so the terms Ri is equal to y minus f of x. So you can see here. Okay, so the difference between these things, okay, are called residuals. So this measure or least square fit simply minimizes the function s, okay, in terms of the coefficients, which is the sum of the squares of the residuals. Okay, now hence the optimal coefficients can be obtained by the solution of the differential equations, the first order differential equation here. Okay, now given we have multiple coefficients, so this will become a partial differential equation, okay, where k is from 0 to m coefficients. Generally, these functions are nonlinear and coefficients a, I may be difficult to solve. Thus, to make these linear, a fitting function with a linear combination of specified function f of j is chosen. Okay, so for example, later we will talk about that in case number 2 in the polynomial fit. Okay, where f of x is an m degree polynomial function with these following equations. Okay, so we will talk about this, okay, the case number 2. So just very simple, instead of purely linear, okay, in terms of a0 of x plus a1x, Okay, so we will have a linear form in this way where we have f of 0 is equal to 1, f1 x, f2 x squared, so on and so forth. So in data analysis, standard deviation is widely used measure to quantify the spread of the data with respect to the fitting curve f of x. So it is defined as this one. Okay, where the sigma here is equal to the square root of s and divided by the denominator n minus n. Okay, if n is equal to m, then we have interpolation and it's not curve fitting, meaning we have our line, our curve passes through all points, which is not the case for curve fitting. And s of 0, or the function s, is equal to 0, making both the numerator and the denominator equal to 0. Thus, the sigma, or the standard deviation, is indeterminate. Okay, so our goal here is curve fitting. We would like to create a curve or a line into data points that can represent those data points, and also to ignore the noise among the data. Okay, so we have this standard deviation function. It's a user-defined function where we input c here. Okay, this is the coefficients, and then the data x and y. And then if you can remember the eval poly, so we have it in the bottom, so we will share. But this one is very simple. Okay, so we're just following this equation, but it would be better if we will talk about the following. Okay, so we have here the sigma. Okay, then this function will simply return the sigma, okay, given the x data, the y data, and c. So how to get these values? Okay, the coefficient, we will talk about that one in the next lesson.